Hey everyone, welcome back to our channel. In today's video, we will be talking about mechanical vibrations, from the strings of a guitar to the spinning of a washing machine, and even the turbines in power plants. All these systems vibrate. Properly modeling these systems is crucial in reducing the risk of failure. Let's start by considering a car moving over a rough terrain. As the car moves, its chassis is connected to the wheels by a suspension system, responds to the uneven ground below. We can model this system by representing the car as a mass mounted on a spring, and in a more realistic scenario, also include a damper. This setup is an example of a forced vibration in a damped system, which we'll explore later. But first, let's begin with a simpler case, a mass spring system with no external force and no damping. By analyzing the free body diagram and applying Newton's and Hooke's laws, we can derive the equation of motion for this system. This leads us to a second-order, linear, homogeneous differential equation. To solve it, we guess a solution in the following form, which isn't as arbitrary as it might seem. Observing the system's behavior reveals a sinusoidal pattern guiding us to this solution. By differentiating x and substituting it in the ODE, we can derive the characteristic equation and solve for s, which gives us the poles of the system. It's important to note that the natural frequency, omega n, of the system depends solely on its physical parameters, mass and stiffness, and it's unaffected by external forces or damping. We can now write the general solution, and using Euler's formula, express it in terms of sine and cosine functions. This final solution is influenced by the system's initial conditions, which are initial displacement and velocity. The solution can also be expressed in a different form to highlight the amplitude and phase of the harmonic oscillator. By calculating these coefficients, amplitude and phase, it becomes easier to visualize the result. With this approach, it's easier to plot in a general form like this, where the slope and x value at time 0 indicate the initial conditions. We can determine the maximum amplitude of oscillation, the phase of the system, and observe that the mass reaches its maximum velocity as it passes through the equilibrium point. This behavior aligns with the principle of energy conservation, where kinetic and potential energy continuously exchange within the system. While this discussion has focused on spring mass systems, the same terminology applies to all single degree of freedom systems. This includes beams, torsional members, and rotational elements like disks or pendulums, where the mass can be substituted with the mass moment of inertia. Next, let's see this concept in action with a MATLAB simulation. I've created a simulation where we solve the differential equation using ODE 45 and visualize the results through animation for better understanding. As expected, we observe sinusoidal outputs. I also developed a MATLAB App version where you can experiment with different inputs and observe how the system's trajectory changes. It's much more user-friendly, allowing you to easily play around with the inputs and see the effects in real time. So that's it. What other topics would you like me to do on next videos? Let me know in the comments. And if you enjoyed the video, please give it a thumbs up. Don't forget to subscribe and hit the bell so you won't miss any future content. Thanks for watching.